Okay. Now, let's leave ICD for the moment. I just remind you what is Auger. You ionize a core. You have a local ejection of electrons, 1 or sometimes 2, and ICD, where it goes through the neighbor. So you ionized 1 in the valence, then you have A plus B plus, or neutral. I've shown you also after excitation. It doesn't really matter. Now, originally, we discovered while we studied ICD that there is another process. It came out from the calculations, and the process we called ETMD. I will explain in a moment what it is. The meaning of, it's written here, Electron Transfer Mediated Decay. So you have a hole, the same state, but you have a different neighbor. It must be a different neighbor. Now, the neighbor donates an electron, neutralizes this excited state, and the excess energy, if there is used to kick out another electron. So you start with A plus B, and you wonder, A becomes neutral and B double plus. Okay? So now there is ETMD 2 and 3. 3 means that 3 bodies are involved. So one donates this one now donates this electron to neutralize this one, the one which carries the original excess energy, and the energy is then transferred to a third neighbor, like ICD, if you like, and kicks it out. So you have A, B plus C, and then you have A plus B, C plus. Okay. Now we thought it's great, but we found out that the process has a relatively low probability, and I'll explain that things have happened, what has happened, and how do you solve the problem. That ETMD becomes very important. Now, let's look at energy transfer versus electron transfer. So ICD, which is energy transfer at large distances, it's energy transfer, and ETMD, which we saw you have to transfer an electron, so it's charge transfer or electron transfer. Now, this is a log-log plot. This is an ab initio calculation on magnesium neon plus, where you ionize a 2s, like we had before in the dimer, just 2s, where there is no Auger, nothing, just it will take a nanosecond to emit a photon, and we are faster here. That you see, it's much larger, and then it goes to some asymptotic value, and this is the analytic calculation, which you can do analytically at large distance. At large distance, you can show that the gamma, the rate, is 1 over omega, so the excess energy to the power of 4, which tells you that the smaller the energy, the excess energy, and you can still ionize the neighbor, the better. Then it depends on, of course, on the ionization, photoionization cross-section of the neighbor, which you want to ionize. This is very intuitive. It's like a photon, and it's indeed called virtual photon. So no photon is involved, but the mechanism, if you calculate it, you see it looks like a dipole transition, like as if there was a photon, so which is called virtual photon. Now it's also dependent on the inverse radiative lifetime of this state, so it was 1 nanosecond. But what is surprising here, at least to me it was very surprising, that the faster the radiative decay would be, if the atom would or molecule will be isolated, the faster it is, the faster ICD is. Okay, so this is something which I always find a bit counterintuitive, but of course it's true. Now let's go to the other side, electron transfer. Of course, electron transfer can only happen due to overlap of wave function. An electron cannot just jump somewhere, I mean, only in fairy tales, but you need an overlap of wave functions. Okay, so overlap decays at large distance exponentially. That's well known, so I expect that at large distances, the gamma, the rate for the ETMD falls off exponentially. Now, this is logarithmic log-log plot. That's why you see here slope of 6 or minus 6. Here it's logarithmic, but this is a linear plot. So exponential is this. And this is the ab initio calculation. And this is the same ICD plot, which is of the rate, which we put here on this scale. So you see it can be orders of magnitude larger. So energy transfer is usually much more efficient at large distances. At short, they may cross somewhere, but the equilibrium distance is 4.4, I think, of 3 angstrom. So they are really hanging around quite large distance. So there, of course, energy transfer is much, much more efficient than the charge transfer. So this was the reason why we thought that because electron transfer is much faster, energy transfer is much faster than electron transfer, we thought you will only see ETMD when there is no ICD. People made nice experiments where you had both and they could see it because the product is different, so they could distinguish. But then we forgot about it. I thought it's not so relevant, it's weak, so we forgot about it. But there are experiments on that, what I've shown you. So now the next step was indeed that again, all of a sudden, I realized that I was mistaken. I took the same states, you see, which do ICD, and I looked how important ETMD is, or electron transfer. But why not take a state which not at all can undergo ICD or anything else? Let's take the ground state of a cation. Here is a cation. It doesn't matter. The ground state of a cation, or dication, sorry, 2 holes. So that would be a product after Auger. We know there are dications formed. Some have high energy. They will undergo ICD with a neighborhood. But the ground state is well populated and is, for example, a stable system. But now if I have it does not have any excess energy. But if I have a neighbor, again, the same can happen what I showed you before. The neighbor can donate an electron. Of course, depends on the energetic. So the neighbor can donate an electron, neutralize one charge, so A double plus becomes A plus. It doesn't have to be double plus. It can be 3 plus or 1 plus, but an ion is favorable, of course. Then there is enough excess energy gained from the neighborhood, so to say, not by itself, and it is used to kick out an electron from the donor, from the one who donated. So at the end, I have A plus and B double plus. And of course, you will have a Coulomb explosion. And this is, you see immediately that this is the dominant process because there is nothing else. Now, a nice example is the dramatic enhancement of single photon double ionization. The single photon double ionization has been studied by many people because the photon interacts is a one body operator, so it interacts only with one electron. Okay, so you would expect naively that the photon kicks out one electron if you ionize. Okay, now the electrons talk to each other, so if you take one out, maybe another one wants to accompany it. So this is due to electron correlation, so electron effects. And that's why, because electron correlation is very interesting to understand, that's why many people have studied double ionization with a single photon. Okay. Auger process, you take away an electron, and then there is a decay of that system. Okay. Here, the photon takes 2 electrons out. Of course, it can also be rather complicated, all the individual mechanisms which can take place, but in helium, for example, they just would go out. Yeah. So now let's take an example where you see that ETMD can play a role in this single photon double ionization. Let's take magnesium, because we understood it's for us how to calculate it. So magnesium, and you put near it a helium atom. You have a helium. We all know helium is the most inert system. You would not think that something can happen. Now, if I take a photon which has sufficient energy to double ionize the magnesium, you have some probability to double ionize with one photon the magnesium. The helium doesn't interfere here. But this photon can also ionize the helium. Okay. Now, if you ionize the helium, The magnesium will undergo with a helium plus, it's a lot of energy, will undergo ETMD, so it will donate one electron, and the excess energy, it's quite a lot, it's 25 eV, will be used to kick out another electron from the magnesium. So at the end you have the same magnesium 2 plus and a neutral helium, and if you don't measure the electrons, you think that the helium just was standing there, but the cross-section grew by 3,500 times, okay? Because the ETMD is much more, so to say, efficient or probable than the direct double ionization by a single photon of magnesium. Okay, so you see, even helium can be a very nice partner for nice inter-atomic or intermolecular processes. Okay, now again I asked Till, who can draw so nicely, I cannot do anything like that, to make some cartoons for me, and this is what he did. So ETMD2, just to remind you, or to so you have a cartoon in front of your eyes. Let's say it's a dication, and the neighbor gives an electron, and this energy gain is used to kick out an electron here, and then you have a Coulomb explosion. Then ETMD3, I took here rather a single cation, one donates an electron, the energy is then transferred, and it's again like a virtual photon and kicks out an electron here. Then you have these two are, this is now neutral, and these two are charged, and will probably also fly apart, depending on the system. Okay, so ETMD is really the dominant relaxation pathway if you have outer valence ionized ions in a medium, because there is nothing else which can really interfere here, depending of course on the neighbors. If the neighbor is difficult to ionize, then that would not like to transfer an electron, it will not happen, but it's only due to energy, not due to the fact that it will happen if the energy suffices to do the process, then it happens. Now it's important in neutralization mechanism, particularly of multiple charge ions, which are produced, for example, by Auger in a medium and so on. Now a little about scaling with equivalent neighbors, else it's more complicated, of course. ICD we have seen in the neon clusters, you expect something which gamma will go with n, the number of neighbors. Unless you have coherence, then it can be much more. We have seen that a single neighbor, but you have many which participate in the excitation, also can give a factor of n. Now ETMD2 scales also similarly, and ETMD3 is actually for large, if you have many neighbors, a big winner, because it goes by pairs. You need 2, and the number of pairs, if you have many neighbors, it goes as n over 2, which, let's say, if you take 10, so this will be 10 times, and this will be 10 times, and this will be 45 times. So if you have many more neighbors, who knows, yeah? But of course, it's getting more complicated because of screening and many problems, depends what kind of systems you have. Okay, so I would like to actually to close with an example where both ICD and ETMD happen, and where there are really new experiments now. Last year something appeared, and there is an experiment which is on the way. I mean, it's written and submitted directly to this, and the others similar. Now, I would like to discuss which we call X-ray induced photochemistry. Okay. It's metal ions, so I'll explain in a moment, but just try to think that you have a system like in your own body, what I show is also present in your own body, and it absorbs a single X-ray photon. What can happen? Okay. Of course, it's a metal atom, metal ion I'm talking about. I'll explain how the metal ion comes about. And this is our model system which we calculated. So it's magnesium in water, and magnesium in water forms something like that. So 6 waters will be around magnesium 2 plus. So magnesium gives away 2 electrons to somewhere in the big system, and that's a stable system now. Magnesium 2 plus and 6 neutral waters. And the experiments were done with magnesium and aluminum with lithium, so all metal atoms in real water. Okay, not in this, but in real water. But we cannot calculate real water. But this is the maximum we could and maybe still can do. Okay, so that's the idea. You have magnesium 2+ in 6 waters. So we know that the number of neighbors makes a lot of difference, and this indeed is the case. Now, this looks a bit busy, but it's simple. I will lead you through it, so don't be irritated. Now, here are the time scales, and here is what happens. You have, I only wrote down the magnesium. You have magnesium 2+ in the ground state, surrounded by waters. Now, with a single X-ray photon, you ionize the magnesium 1s, and you get magnesium 3+. Then there will be Auger. We calculated the rate. It's about 1.9 femtoseconds. So very fast. Okay, and Auger gives several channels, actually many, but these are the 4 most populated channels. This, that, and that. If you can read it, it's good. If not, it's not a problem. It's a story which comes from the calculation. So Auger electron is emitted here, 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 and here with some propensity. Yeah? So only one step happens in every case. So these are the states which are produced by Auger. So 3+ it became due to ionization with the X-ray photon. 4+ now it's 4+ due to the Auger. So we have now 4+ ion in water. Okay. Now this state and this state can undergo ICD, and to our big surprise, we calculated it in different ways. It's even faster than the Auger. It's at least in the calculation. I mean, it's sub femtosecond. Okay, so it's very, very fast. You go from here to here, and of course you produce slow electron, which we said is damaging, and you produce a water radical, water ion. Okay, here and here. So each does it. Now the energy is not sufficient. Now we are here and here. The energy is insufficient for ICD, but not for ETMD. Now ETMD can take place. You can go here and here, and from here only here to these states. ETMD neutralizes, so now it becomes 3+, but you produce another ETMD2, another 2 water radicals in ETMD3, sorry, and ETMD2 water double plus, which will fragment, but we don't calculate it. Okay, now, so we are here, and here, and here, and now ICD here is again open. This ICD is a bit slower. It's now 2 femtoseconds. ETMD, you see, is much slower than that, but still fast because of the number of neighbors. Now, so ICD will happen. You again produce a water radical and a slow electron, ICD electron, and now you are here. You are 3+. Now ETMD can happen, and you again, by ETMD 2 or 3, you produce 2 or 1 of these ionized waters. And where do you end? Magnesium 2+, where I started. But now you have to imagine, you are surrounded by waters, the water become ionized, they fly away, okay? Because the magnesium, they fly away, and new water comes. So now, after rather short time, we estimated about 200 femtoseconds, everything is ready for the next hit. So I hope, I got scared when I saw it myself, because I thought, oh, okay, but there must be protection mechanism in the body, I think, otherwise it will be a disaster. Now, so every photon leads to a full cascade, as you have seen, which is finished very fast. The lifetimes are much faster, but this is the estimate where really the process is over. On average, you produce 4.3 radicals and 2.4 slow electrons. Its probabilities which way you go, per a single vacancy produced by a single X-ray. Okay, and then you have Coulomb explosions, it's additional energies, and at the end, magnesium ion reverts to the initial state. Okay, so it's a cycle. So it's a damaged cycle which happens, and luckily the experiments have been done now and show exactly that. I don't want to read all of that to you. One point is that we found literature that people try to estimate the damage by the change of charge on the metal ion. But you saw it reverts back and the damage is enormous. So it's not this what plays a role, whether at the end you have magnesium 3 plus instead of 2 plus. This is not the point. It can revert back to what it was in the beginning, and the damage can be very large. And of course, we have everywhere magnesium or calcium or whatever, all of these metal ions in the body, close to DNA or whatever in water and so on. So this we didn't study too carefully what happens more. And nearly closing, I just want to say what I didn't talk about. There is work of ICD in strong fields like free electron lasers, and then there are other variants of ICD like double ICD and so on, which collective ICD, which I've shown you from this surprise which was done here experimentally, that 2 or more have to simultaneously transfer the energy. This is still in development. Time evolution of ICD, there are experiments and theory. Okay, ICD quenches many processes because it happens faster than something else, and then you quench dissociation, for example. Isaac will hear tomorrow. It's a subject by itself. There's also vibrational ICD, doesn't have to be electronic, and methods of computations I didn't talk about. And now I think it's really an open field. There is much we don't really understand. So we know very little on ETMD, nearly nothing about Isaac except of calculation. There are no experiments here. In ETMD there are, but it's limited compared to ICD. But it's clear to us that it's very relevant in nature. And in ICD, I just cite Kiyoshi Ueda, who was one of the experimental pioneers. He wrote in his papers always, ICD is everywhere. No, it's of course not everywhere. You need excess energy. I liked it. Okay, and there are many, many people who contributed, so the slide is full, and not everybody is on it, but this is the situation, and I would like to thank you for your attention.